Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, can we trust that rover? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and in the first episode of the new season, we're returning to the fascinating field of space robotics. This time, focusing on planetary rovers and the new AI advances that are making them more intelligent and adaptable than ever. Before we get started, I'm going to launch this season of Robot Talk with a bit of brutal honesty. I'm sad to say that the future of Robot Talk is uncertain. For the past 5 years, I've been extremely lucky to receive funding to produce Robot Talk. First from the UK RAS network, and more recently from the Hamlin Centre at Imperial College London. However, my current funding is due to finish next summer, at the end of Season 6. And right now, I don't have enough money coming in from other sources to cover the costs of producing the podcast. It sucks to have to say it, but it's true. I'm so incredibly grateful to everyone who's supported Robot Talk by joining the community on Patreon. I can't thank you enough for your generous contributions. But at the moment, the supporter contributions just aren't enough to cover the costs of producing this podcast. As I'm sure you can imagine, as well as basic operational costs like web hosting, it takes a huge amount of time and energy to make each season of Robot Talk. From researching guests and planning interviews, to editing audio and promoting new episodes. So this is my plea to you, my wonderful Robot Talk listeners. If you're in a financial position to support the podcast, and I totally understand that not everyone is, then it would mean the world to me if you could chip in a few pounds or dollars a month on Patreon to help secure the long-term sustainability of the podcast. You can sign up on patreon.com/Claire Asher from as little as £2 a month. If you can't afford to help out financially, you can still support the podcast by liking and subscribing on your favourite podcast provider, leaving a review on Apple or Spotify, or just simply sharing the podcast on social media and telling your friends about it. More listeners, subscribers, and positive reviews puts me in a better position to find sponsorship, so it really does make a difference. And a quick shout out to my new Patreon supporters, L. Poocher Elkins and L. Thank you so much for your support. Welcome to the Robot Talk community. So, with all that said, I'm excited to introduce this week's guest. I recently had a thought-provoking conversation with Frances Zhu from the Colorado School of Mines about intelligent robotic systems for space exploration. This week, I'm chatting to Frances Zhu, an assistant professor at the Colorado School of Mines, who's developing intelligent robotic systems for space applications. Hi, Frankie. Wonderful to have you on the podcast.
Hey, Claire. Great to be here.
So you lead the Robotic Space Exploration, or ROSE lab, at the Colorado School of Mines. So can you tell us a little bit about the research that's currently going on in your lab?
Absolutely. So generally, we study how robots move and think about movement in space. So involved in the thinking are algorithms that are aiming towards intelligence in mobility. Right now, our lab is really interested in rovers, but we have historically also worked on orbiters and satellites.
Fantastic. I'm absolutely fascinated by space robotics, so I'm really glad to have you on the podcast. Especially because a lot of the people I've interviewed previously focus on kind of satellite applications, which are really, really cool. But I'm excited to kind of dive into the planetary rovers and stuff like that.
Absolutely. I made this transition because, yes, satellites and orbiters are definitely one of the first steps that we can observe from space. But I just really wanted to get into the environment. In the field, we call it in situ. And so I really wanted to see through the eyes of a rover that was really embedded in a space environment.
Yeah, absolutely. It's kind of a really exciting opportunity to explore like a completely unknown world.
Absolutely.
So you're working on algorithms to help robots autonomously navigate and explore these extreme, remote, and unpredictable environments. So can you talk a little bit about how planetary rovers are controlled right now, and how AI approaches like machine learning are helping you to expand their autonomy for future missions?
Yeah, absolutely. Great question. So space robots have historically had a long history of being operated from Earth. But as we venture further into the solar system or even into interstellar space, our robots have to get increasingly autonomous. We can still feasibly control rovers on the moon through teleoperation, but there's a communication delay. We've actually seen one of the historical Russian rovers called Lunokhod, and it had cameras on board that was streaming video feed back to operators on Earth.
Okay.
But as we move to Mars, for example, where there is 7 minutes of delay, operating a rover doesn't make sense from Earth. A lot of the rovers that are on Mars have more autonomy, especially when it comes to their mobility, because the timescale for the dynamics interacting with the ground and the rover, that's much faster than 7 minutes of reaction of communication. And so, for example, Perseverance is one of the most treasured autonomous rovers. Its autonomy algorithms, led by NASA JPL, it's called Autonomy, has enabled Perseverance to traverse kilometers without any kind of human intervention. And so that autonomy, it involves this pipeline, an autonomy stack of perceiving an environment, propagating your dynamics, predicting where you're going to go, path planning, which is telling the rover where it should go, and then the control, which is matching where you think you're going with where you want to go.
Right.
So executing actuator commands. So yeah, that's generally how we do it, but we could always do better. There is uncertainty in our dynamics of how rovers move between the terrain, and that's something that my lab really focuses on, understanding this field of terra mechanics so that we can get better vehicle state predictions.
Okay. And so at the moment, if the rover encounters something that it doesn't know how to deal with, then it waits and sends a message back to Earth to say, help, tell me what to do.
That's exactly right. Yeah. So our rovers are not the smartest when it comes to making their own decisions. They can navigate through a predefined set of environments that are considered safe. But as your uncertainty grows, you run into situations where the rover is uncertain how to deal with the environment. It has to send telemetry back to Earth, and then the human operators make a decision and update the rover's commands to get it back into a safer trajectory.
And how do robots know where they are on another planet? Because on Earth, we're very used to using GPS, but they don't have that luxury.
That's exactly right. Yeah. So we don't have the GPS infrastructure on the moon, on Mars. And so we rely more on the assets that are there. So Mars has reconnaissance orbiters, there's the MRO, and the Mars Reconnaissance Orbiter is constantly imaging the surface of Mars.
Okay.
It's constrained in its flight trajectory, so only ever so often does the orbiter see the rover on the planetary surface, but every time the orbiter does see the rover, humans on Earth get that image back, and then we can figure out within that image where on the surface the rover is. But the rover also does its own localization. So the orbiter is offering what we call global localization, which is where is it along the planet. But then the rover does its own internal updates of relative localization, which is how far have I moved from my previous position.
Mm-hmm. Okay. I've spoken to roboticists before who do robot localization on Earth and learning landmarks that they see. I'm guessing there are fewer distinctive landmarks on Mars.
Yes, that is exactly right. So on Earth, we call these kind of environments, especially urban environments in which you have buildings and trees and distinct landmarks like sculptures and stuff, those are great features that you can leverage in localizing yourself. But on the Moon and Mars, if you can close your eyes and imagine yourself on that surface, all you see are the silhouettes of ridges. You can see craters. But other than that, the features are quite sparse. In fact, the rolling hills of the Moon or Mars, in that certain lighting condition, don't have many distinctions. The features are quite diffuse. And so a big question is, how can we perceive environments and localize our rovers better on these planets without any kind of external reference?
Mm-hmm. Is that something that you're applying machine learning to?
Yeah, absolutely. So I would say previously you were asking about AI and machine learning. And so we've seen huge progress in AI and machine learning models in computer vision, where machines are much better at identifying objects, much better than humans. We call this AI superhuman capabilities. And there's a really cool infographic of the progress of AI doing certain tasks better than humans. We have definitely breached that threshold for AI doing better than humans in computer vision since 2016. So it's quite obvious for us to adopt computer vision into autonomy pipelines. And so it's almost like a baseline that we use computer vision models on board our robots to do this kind of feature identification and extraction.
Mm-hmm. So obviously, a major concern around the use of AI in robotics generally relates to kind of the issues of transparency and trust. So, if we're using AI rather than traditional programming approaches, is that AI transparent about how it's making decisions, why it's making decisions, and can we trust it to operate in the way that we expect it to and safely? How do you address these kind of issues in your work?
Yeah, I think we have to set up the attitude of aerospace engineering before we can even address trust. In aerospace engineering, for space missions, we are so keen on these missions succeeding. And so we have very low risk tolerances. So we really bank on the robot to behave as we expected. We really need guarantees that it's going to do what we want it to do. And so for those reasons, we highly depend on trust in the robot. When it comes to translating that into software, we have historically hard-coded a lot of behavior into robots to cultivate that trust, to increase transparency in the behavior of the robot. But as we move into AI and machine learning, I'm sure that you're hearing all this news about how can we trust these models. These models have millions or billions of parameters, and we humans cannot hold all of that information in our head at once to interpret what this AI model is exactly doing. In fact, we've seen a lot of applications in current day that are much more human to AI interaction with chatbots. And you see a lot of hallucinations, you see very sporadic, random responses sometimes. And so in aerospace engineering for these space missions, we don't want to have any of that hallucination. And so I think I would love your thoughts on this of how do humans even cultivate trust with anything? I think humans depend on exposure, whether that is the magnitude of interaction or the length of interaction. And so we are trying to, my lab is starting to go into this field of how can we cultivate more trust between humans that are operating the mission and robots that are out in space doing their own thing. But do you have any suggestions for trust in robotics?
Yeah, I mean, like you said, the way that we trust people is based on the kind of repeatability of interaction, of knowing that, every time I talk to this person, they act a certain way, or, I can anticipate their behavior, and, you know, they haven't yet done anything bad, or, anything that I've asked them not to. So I guess, testing these robots on Earth helps, but they're still potentially going to encounter scenarios on another planet that we can't anticipate and we can't plan for, which makes it really, really challenging.
Absolutely. And one way to mitigate against those challenging situations is that I was listening to a talk by Terry Fong, who is a role model of mine. He's like the chief roboticist at NASA Ames. And I asked him this same question. He said, to increase transparency, robots need to send pertinent information in a timely manner. We need to be able to visualize what they're doing, to embody that state of mind. And so, like humans have eye contact and they're looking at certain things, they have body gestures, so you can anticipate how they're feeling. I think we need similar analogies for robot interaction.
Yeah. And the other aspect of it I was thinking about was, if a person does something, I can ask them, why did you do that? And they can talk me through their thought process. So having that kind of explainability of a robot to say, I saw this, so I did this. And to know that it's telling the truth and kind of giving you the whole picture, I guess, is important.
Absolutely. And that whole picture, it's hard to communicate. Like imagine you're over a walkie-talkie, your robot, which we'll just pretend is a human, that is far away in an unseen environment, interacting with physics that it didn't really know ahead of time. Mm-hmm. How do you communicate those instructions? And then how then does that human or robot in that remote location communicate back to you? Can it tell you everything that you need to know so that you could help it?
Yeah, and it may leave out information that it doesn't think you need to know, but you feel that you needed to know that. This happens with people as well, right?
Yeah, absolutely. But imagine that all of the personality, the instructions that is on that remote robot or person, that was all defined ahead of time. So how can you even anticipate the kind of behaviors? I think we need to see more adaptability. I mean, it's impossible to adapt the hardware of the rover as we sent it, but more adaptability on the software side, on the personality side.
Yeah. Years ago, I was in California, and we were on a geology field trip, and just by chance, we bumped into somebody who was testing, I think it was a Mars rover out in the desert, because they said this is the closest analog to Mars that we have on Earth. Do you have like places like that you test rovers that are similar to Mars?
Yeah, that's a great question. And another reason why I wanted to get into rovers more is to go on field trips to do that testing, because it's quite boring to test satellites in simulations. I love satellites. They have their use, but for my personal selfish interest, I wanted to go out to the field because I love nature. I love the mountains. Where we typically go, so Colorado is where I'm at. It is quite arid. There are locations where there's not much vegetation. Those are things that I look for. There's an international challenge called the University Rover Challenge, and they host their competition in Utah at the Mars Desert Research Station.
Okay.
And so if we were to find a really good analog, I would probably go to Hanksville, Utah, where the competition is held. But there are different analog environments for different purposes. We also see in Hawaii, for example, there's the high seas habitat, which simulates astronaut interactions in remote locations. And so I think there are many different locations that look like places in outer space. It just depends on exactly what you're trying to simulate.
Yeah, fair enough. So aside from the kind of trust issues that we've just been discussing, what do you think are the biggest outstanding challenges in robotics for planetary exploration?
I think I could answer this in different layers. The biggest challenges in space robotics right now, yes, it has to do with trust, but I think it has to do with scaling the number of robotic missions that are out there.
Mm-hmm.
A bottleneck for scaling is the human touch. Right now, we need a lot of human operators to operate these space robotic missions. Another bottleneck is that all of our interactions have to be funneled through a deep space network or some kind of ground station network that you have to schedule through.
Mm-hmm.
And so if there is some amount of human touch, it has to go through that bottleneck. But to scale, we need to minimize the amount of time that we schedule through these communication networks, minimize the amount of time that humans are in some kind of war room thinking about the strategy for a mission. We need to punt a lot more of that planning on the robot itself so that we can have more robots in space.
Mm-hmm. Yeah. I always like the fact that, Mars is the only planet that we know of that's exclusively populated by robots. I wonder, can we get to a point where it's not just populated by individual robots doing their own thing, but, a kind of society of robots all working together and communicating and collaborating with each other to help them plan and cope with the environment and do the science that we want them to do.
I would love that. Yeah, that is a dream of mine as well. And I think what's beautiful about robots, they're pros and cons. They don't have the same emotions that we have. And so that's the good emotions, which is this hope and ambition for, I don't know, self-enlightenment.
Yeah.
They're already at the state that they're going to be at, but they also don't have the bad personality traits of like envy and selfishness. I think that we can certainly encode a type of ideal in the way that robot networks behave and manifest our dream through our code. Sorry, that was cheesy.
I know that they don't have emotions, but it's very, very hard not to anthropomorphize these little planetary rovers.
Absolutely. And I think a way of understanding them is through anthropomorphizing, through making analogies. And that's certainly how we make advances too. A lot of roboticists are in a field of biomimicry where we're very inspired by biological creatures. So I think there's a lot to learn there. A lot of machine learning models are fashioned after, they're called machine learning models. A lot of them are artificial neural networks, but for us, they're biological neural networks.
Yeah. So, I mean, I know we've talked about Mars. I know you've done some work with lunar rovers as well. But if you had like your dream planet or, moon that you could explore, what would it be?
Oh my gosh. Okay. I'm going to give my answer, but I would love to hear your answer as well. I would love to pursue this question of life. I think that is such an existential question for humans, and I think there are two ways to go about it. You can send a mission that is looking for life that looks like us. And so that would be more water-based ecology systems, more carbon-based organisms like Europa and Enceladus. But you could also go about it a different way, which is if we were to look at the periodic table of elements, right underneath carbon is silicon. And so there are silicon-based ecosystems, methane-based weather cycles on Titan. And so I am super, super excited for the Dragonfly mission, where we are not just pursuing life that looks like us, but pursuing life that potentially looks very different from us. Where do you want to
go? Well, I mean, yeah, I agree with you completely. I always think that it's a very narrow view of things to assume that life should be water-based, that it should be carbon. So yeah, I mean, that would be very high on my list as well. Yeah, I mean, I was going to say like Europa or somewhere where we think that there's these oceans under a layer of ice. I think it would be really, really cool to explore those. I mean, there's so much about our own oceans we still don't know, but to see an ocean on another planet, that would be cool.
Absolutely. And we want to target specific areas in these very cold places. Unfortunately, life is a little less probable in these very cold places because cold is equivalent to less energy, and life needs energy. It needs either heat, it needs a distribution of chemicals that are friendly to it. Yeah, the right chemical composition. These are really important questions to the formation of life.
Yeah, definitely. So we had a couple of audience questions submitted by Robert on Blue Sky. So the first question Robert sent in was, how does development in the private sector compare to public sector advances in the field?
That's such a good question. So I'm teaching a space robotics class right now, and we talk about this quite frequently because a lot of my graduate students are industry professionals. And so when we think about an aerospace engineer, we typically think about NASA. We think about like the Apollo program, where NASA centralizes all of the expertise for space missions. But we have since diversified. It started with launch vehicles and the versioning of these new space companies like SpaceX, Blue Origin. And then we've gone even further down the commercial route of, we're calling this program CLPS, Commercial Lunar, I forget what the P and the S stand for, but there are multiple companies that have won contracts through CLPS to land landers and rovers on the moon. And these companies include Honeybee Robotics and Astrobotic. There's way more diversity in the kind of entities that are participating in space these days. And so if I were to draw a dichotomy in where the government fits in the space economy versus these commercial companies, the government has achieved some really great things in history through the Apollo program. They have continued to contribute in scientific missions. But then there is the inherent nature of organizations where they accumulate more bureaucracy and they're less risk tolerant. And so while NASA is still doing incredible things, I think that some types of missions are quite burdensome. And so we've seen a shift in responsibility of the government in launching assets into space and now landing assets onto the lunar surface. We've shifted that responsibility to these other companies, because these kind of capabilities we need to repeat. There is an amount of stamping it and just pushing it out the door over and over again. So these companies, they have taken a higher risk posture in that they are more comfortable with failing, especially at the beginning. It's almost an expectation. For example, SpaceX didn't exceed 50% success rate until maybe a couple years in from their founding, but now they're quite reliable, 90 plus percentage of success in actually inserting their assets into the desired orbit. And so we're going to see that with CLPS as well. Right now, the landers are not succeeding, but we as a community tolerate that because they are a commercial entity. I think that us as a public community tolerate that much less when it's a government-led mission.
Yeah.
Do you feel that way as well? I mean, I know that we live in different countries, but the attitude towards government versus business.
Yeah, that's interesting. I definitely see that side of it. The other day I saw a YouTube video where someone was talking about there'd been quite a lot of recent failures of one aspect of what SpaceX were working on, and that shareholders were getting nervous. And so I guess there is always this risk that if the shareholders lose faith, then the whole thing kind of falls apart. Whereas I guess with government, provided that the government continues to see the purpose of the funding, maybe they're less likely to abandon it. I don't know. Yeah, there's so many factors. And I think if there's a sudden kind of economic turn, I feel like either side might just abandon a project.
It's funny because, yes, as you were saying, SpaceX is facing backlash from recent failures. It seems like they are old enough for people to have higher expectations for them. Yeah. I think that is the curse of the government. Even though these engineers are of different generations, they haven't lived as long as the entire NASA agency existence. You just assume that NASA has this high bar, this high expectation of success, even though the engineers within them haven't been there that long.
Yeah. So Robert had a second question, which was, what nation state would you say is the current leader in space robotics?
Ooh, I think that the U.S. is still the premier aerospace country, just based off of historical inertia. I think we're still sending very ambitious deep space missions. But when it comes specifically to lunar exploration, I'm really excited by China. Not in a political sense, but in their technology.
Yeah.
They have accomplished so much in their lunar exploration program. They have sent landers. They have sent rovers to new places, like to the far side of the moon and to the poles. They've even sent samples back from the moon through a totally robotic mission. So I think they're just launching and succeeding at a cadence that's much higher than the US and with technological capabilities that are also unprecedented.
Yeah, absolutely. I see a lot of cool things coming from ESA, the European Space Agency, but of course that's a whole continent essentially collaborating, not individual countries.
Yeah, I really love the work at ESA, and there's a rover mission I'm really excited about called MMX. The folks who put the sensors and thought about the dynamics of that rover was the German Space Agency, DLR. It's a small community in which I specifically work in like terra mechanics for space robots, but they do really excellent work. They put cameras underneath the rover to inspect the way that the wheel is interacting with the terrain. And no one has done that so far, at least not that they've shared. And so I'm really excited for their data.
That's really cool. Frankie, it's been lovely talking to you today. I've been speaking to Frances Zhu from the Colorado School of Mines. Thanks, Frankie.
Thanks, Claire.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. And check out @Robot Talk Pod on social media to see a photo of a robotic rover competing in the University Rover Challenge Finals at the Mars Desert Research Station in Utah. Next week, I'll be chatting to Ali K. Hoshiar from the University of Essex about making microrobots move. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.